turn these lights off, or are they totally on motion sensors? Because they're bright and the screen's dark. If we turn the lights off,
we don't have that control.
No idea how we control the lights.
That's okay. If they're,
I don't think we have that control.
I don't know that we do. I've never seen lights which I just saw, especially from sitting at this side, it's very bright everywhere else. And if we can't do it, we can't do it.
Yeah, no idea how to do it.
I don't have seats so much.
I've never been.
No, it's not all good. Sorry.
Nice. Hello everyone, welcome to the Center for Astrophysics seminar. Today we have our own ARC DECRA Fellow, Dr. Li Gang, to give a talk about his field. Li Gang obtained his PhD at the University of Sydney in 2020, and he's most well known for his work using stellar oscillations to measure stellar properties, especially internal magnetic fields, rotation and tidal interactions, and the particular type of stuff he loves most is gamma doors. So feel free to take away when you're ready.
Okay, thank you very much. It's my great honor to give this seminar at the beautiful Boom campus. And so today I'll talk about give a very general and fundamental introduction about asteroseismology, the waves, the modes, and also the applications to physics. But don't be scared; this will be super easy. So maybe someone will be curious that why I use the verb listen to stars instead of watching or observe the star. So there's no air in space, so there's no sound at all. And also what we can do in astronomy is just to use a telescope to collect the photons from remote stars. So why should I say listen to them? Because we just use the light variations of the stellar oscillations to study stars instead of just taking one picture. We just take a lot of picture in a time series picture. So that's quite similar to what we hear every day, right? So it's like a new research method to the star. So before I introduce the stars stellar oscillation, again we should go back to the most simple example, that is one-dimensional oscillation. That may be a oscillation of a string. For example, here I just give you a video. So you can see this is a guitar. So if you play it, you can just make some vibrations of the guitar string. So that is an example for one-dimensional oscillation. And also, if you play a flute or pipe, you can make other kind of waves in this situation. So if you just recall what we learned in our physics course or the partial differential equation course, if it's mental abuse. So if we solve the equation of an oscillating string, so we just get some discrete solutions, right? So we call them modes. So there are several new jargons we need to learn. So it's eigenmode. So it's a natural standing wave pattern. So for example, I gave 4 examples here. So on the top, there's a fundamental mode. That means all of the strings are oscillating. But we also can get a solution. It's called the first overtone. So that means we found one point in the middle of the string. One point in the middle of the string that do not show any displacement. So we call this point a node. So a node, that means a position where the displacement is always be 0 in a standing wave. And also we can get the second overtone. So with 2 nodes here. So 1, 2, there are 2 nodes here. And then the third overtone, 1, 2, 3 nodes here. So that's a pattern for a standing wave. So we have this discrete waves instead of continuous wave. And also for each mode, we can have an eigenfrequency. That's the frequency of the oscillation. So one mode corresponds to one eigenfrequency, like this. And if we go back to the video, so let's just select one frame randomly. Yeah, you can see now this is looks like quite sinusoidal, right? It's like a sine function for the oscillation. But in fact, if we go to next, if we select another one, it's like a lottery. So so we need to be very lucky. Maybe this one. So if you look at the second string here, so it's no longer sinusoidal, right? So in fact, in one oscillating system, what we can observe is a superposition of many eigenmodes instead of just one eigenmode. So it's just for example, in this one-dimensional string, we just observe the sum of so many sine terms. So and also it is the same in the star. So in one star, it can also oscillate in multiple frequencies instead of only one frequency. And the combination of this eigenmodes just decide the sound. So decide the sound. So if you play the guitar, you can excite fundamental modes, first overtone, second overtone all together. And some skilled guitar players can select to excite only the harmonics, only the first overtone. So the pitch is higher. So the pitch is one octave higher. So it's quite interesting. I tried to learn guitar, but I found it's hard to learn guitar vibration than stellar vibration. Okay. So now we can go to a two-dimension space. So that is called Kaleidny plate, right? It's the pronunciation. So if we go to the video like this, so it is just a plate, but it's oscillating plate driven by a vibration exciter. But I think in our fundamental physics experiment course, we just use a violin ball to excite the oscillation, right? So and you put sand or salt on the plate, and you let the plate oscillate, and you can find so many different beautiful patterns, right? So many patterns here. So we can see this pattern just because the oscillation of a plate is also a standing wave and also show nodes. So if you still remember, the nodes means the place where the displacement is always zero. So the sand can stay along the nodes. So that means because there's no oscillation. If not, the sand just bounce away. And in this 2D oscillation, the nodes are no longer a point. Instead, it's a line. So we call them nodal lines. So that's how we see this beautiful pattern. So this one, and also each mode corresponds to a frequency. If I turn on the audio, you can hear the sound, but there's a warning at the beginning. So so I select not to do that. Okay. And I'll give you another example for the 3D oscillation. So that is a floating droplet. So when I watched this video first time, I thought it's taken in a space station, but in fact it's not. It's just using some technology to make the droplet floating. And we also can excite oscillations for this one. So it's a true 3D oscillation of a droplet, and we can have so many different oscillation modes here. So fifth harmonic or sixth harmonic like this. So they show different patterns. So different pattern, different modes, and different oscillation frequencies. So that's the oscillation of a droplet. So okay, now we can go to the true stellar oscillation here. So we can begin from a radial oscillate or pulsating modes. So that's called the radial modes because if you look at these animations, the stars just expand and contract uniformly in the radial direction. And on the left panel, so stars are expanding and contracting in the same way. But in the right panel, there's a boundary in the middle of the star. So you can say that the positions are in opposite, right? So the inner part shrink and outer part expand. So that means there is a node inside the star. So there's a node. So we call them a radial node. And we also give a number n, the radial order n. That is the number of nodes along the radial direction. So for example, for the fundamental modes, the n is 0 because there is no node in the star. But someone will argue, oh, the center also show no displacement, so the center should be constant. So it's just in the convention. Someone think n equals 0 is fundamental. Someone think n equals 1 is 0. So it's a fundamental modes. And for this one, is the first overtone. We have a one additional node in the middle. And we also have a second overtone, third overtone a lot. And this kind of radial position can be seen in a lot of classical positors like Cephei, which is the most famous one, and the Lyrae stars, and also some high amplitude delta Scuti stars. So I just recommend people to go to Tom Lab's talk in 15 minutes for more information about this. And of course, we have a more complex situation that's called non-radial oscillation, but it's better. It's a better one because the more complex, the more information it provides to us. So this one, so the star surface are divided into different paths, and the different paths just show different oscillation direction. So it's quite complex, and then maybe it's hard to analyze in this animation. So I just give you a stationary image like this. So we have another two important numbers. One is called the angular degree L. It's a number of surface nodal lines. That means we also find the area on the surface that doesn't show any displacement. And also another one is azimuthal order M. It is the order of nodal lines crossing the equator. So maybe we can select this star as an example. For example, in this star we have one node on the surface that is the equator, right? It's the equator, and we also have one node that is vertical to equator, right? So in this case, the total number of surface nodes are 2, so L equals 2, and there's only one vertical node, so that means M equals 1. So that's how we classify the modes of stellar oscillations like this. So we have so many modes, and also the M value is always smaller than the absolute value of L. So it's quite similar to what we learned for the quantum mechanics, that's the Hadrian atom, quite similar to that. So someone also call them the quantum numbers of stellar oscillations. Okay, so and another important information I would like to see is called the rotational splitting. So that's an important method that we can measure the internal rotation of stars. So the fact is, so if there's no rotation, the modes with the same radial order and angular degree but different azimuthal order M have the same frequency. So it's called degenerate. So they are different modes, but the eigenfrequencies are the same. So it's called degenerate. But if we have a rotation, the degeneracy can be lifted. So and the modes are split. So like there's a cursor. So you can see in this area you can see 3 peaks. They are all L equal 1 modes, but they have different M values. So M equals -1, 0, and +1. So you see this splitting the triplet. So three components because they have a rotation. And the value of the splitting, so how large the triplet is directly connected to the internal rotation. So that's how we measure the internal rotation. We can measure VCI using spectroscopy, and we can measure maybe the surface modulation. But this is the only method, I think, the only method that we can measure the rotation of deeper layers of stars. Okay. So now we introduce so many concepts. Maybe you will ask why we can use oscillations to probe stellar interiors. So here is a very good image. So you can see this it's just a picture of the sun. So inside the sun there are several lines. That means the propagation of the waves. So we have P modes. That means the pressure modes. So the pressure perform as the restoring force. So pressure modes is just the sun. So it's just the sun in the air. So and you can see in this figure the pressure modes can propagate down, but there's a total reflection because the density is too high, and then the pressure modes they bounce back to the surface. So the pressure modes is always be confined to the surface, to the outer layers of the star. And the most frequency are modified by the physics inside the star. So if there's something weird happening in the stars, it can be shown in the eigen frequencies. And we also find some waves inside in the center of stars. So, for example, you can see this line. It's called gravity modes. So the buoyancy are restoring forces, something like the waves we see in the ocean. So it's called gravity modes or G modes. And the G modes are always confined in the deeper areas of the star. So that means in this situation, we know that the different modes are trapped in different layers of the star. So if we observe multiple modes in one star, we know, oh, this mode is in the shallow area, this mode is in the deep area, and we can analyze the physics in different depths of the star. So that's the basic idea of the asteroseismology analysis. So this also gives some detail about that. So why we have this, the trap of the modes. So we have two important frequency. One is the brute Basala frequency N, another is the Lam frequency S. So in this diagram, the x-axis is the radius of a star, and the y-axis is just the frequency of N or S. So in this figure, we know that the pressure modes should be always the frequency of the pressure modes should be always larger than the Lam frequency, so always larger than the frequency S. And for gravity modes, the frequency should be always smaller than the brute Basala frequency N. So that means in the stars, these two kinds of waves are confined in different parts of the star, and for the sun, for example, for the sun, we cannot observe gravity modes because the gravity modes cannot propagate in the outer layers of the star of the sun. So we cannot see G modes in the sun, and what we can see is only the P modes for the sun. Okay. But we cannot hear the stars, right? So how should we detect the waves? That means, so we can just use the light curves to detect the waves. So if the star is shrinking, that means the temperature is higher, but the radius is smaller, right? So, but if the star is expanding, temperature should decrease, but radius is larger. So the total brightness of the star is changing with time. So if if we keep taking pictures of the star and measure the brightness, we can get this brightness as a function of time. So that gives us the observational evidence of the waves of the star. So that we need this light curve to observe the star. And thanks to exoplanets guys, so now we have opportunity to learn stellar physics using asteroseismology. It's hard to persuade people to spend billions of dollars on asteroseismology, but it's easy to do that using exoplanet as an excuse. And so in 2009 we have a very successful mission Kepler. And in 2018, we have TESS that's also running nowadays. And in the next year, we have two important missions. One is Plato, governed by European countries. Another one is Roman by America. So, and in the year after next year, we have a Chinese mission called ET 2.0. That means the second Earth mission. So we have so many telescopes. And we have so many data for both exoplanet and asteroseismology. So that's now it is really a golden age for exoplanet and asteroseismology. And the reason that we really need the space-based photometry is that we really need a long and continuous light curves. So that is an example. So we just if we give two signals as an input, one is two sine function with frequency f1 and f2, and if you plus them together, you just generate an artificial light curve like this. It's quite noisy, but if you do a Fourier transform Fourier transform, you can get two peaks, and you just recover or reproduce the signals you input. But the Fourier transform is not ideal. It's not perfect. Because we have just we have a finite light curve. That means it's not infinite long. It's just maybe 1 year or 4 years or for tests is 30 days. So that means we have the peak is not too sharp. It has a width. It's called frequency resolution. It's 1/t. And also we can observe a spectral window. That is some additional peaks around the central peak. And so if we have a longer light curves, the frequency resolution can be improved. And if we have a continuous light curve, the window function, the spectral window is surprised. So that's why we need space-based data for that. So before the Kepler mission, we can only use the ground-based data, and we have maybe just a 1 week light curve with with maybe 18 hours of the day with no data, with the last gaps. So in that date, we can do nothing for Asteroseismology. But after Kepler, we can do a lot for that. So now people just discover so many variable stars or pulsating stars along the HR diagram. So you can see for the sun, we have solar-like oscillators. And for right giant and the semi-regular, we also have solar-like oscillators. And along the main sequence, we have so many pulsating stars. And we also have like Cephei star and R Lyrae. And even for white dwarfs and some SDB, so just a helium burning core star. So we also have pulsations from that star. So that means the Asteroseismology indeed gave us sufficient opportunity to research the stars at almost at all kinds of evolutionary stages. So, but for my personal research, I focus on 3 kinds of stars. One is solar-like oscillators, and also data security and gamma dose stars. So, I think maybe more than half of the Asteroseismology guys are working in solar-like stars. So I just spent most of time to introduce solar-like stars, and we just spent the last part of time to introduce data security and gamma dose stars. So here is a power spectrum of solar-like oscillators. So if you get the light curve and you do the Fourier transform, and you just get this power spectrum. So each peak corresponds to 1 mode of the star, and we can find a very beautiful bell-shaped profile for the amplitude. And the center is called mu max. That means the frequency where the power is the maximum. So that is a typical shape for solar-like stars. That's what we see for our sun and also for other solar-like stars. And if you zoom in, you can find the peaks are regularly spaced, right? So the distance between each 2 peaks looks quite similar, right? They just repeat in a certain distance. So that's called frequency separation, delta nu. And this is it's a very important relation called asymptotic relation. That means the peaks are equally separated in frequency for p modes. So, and this value is very important because the delta nu is linked to the square root of mean density of the star directly. So if you have mean density and you have other observational quantity like temperature or luminosity, then you can calculate the mass and the radius. So that's a very good application to stellar physics, and it gives us a very accurate and model independent measurement for that. Also, we can just we can decide, we can find the evolutionary stage of a star using Asteroseismology. So that is example in an open cluster or maybe globular cluster. So they have 10 stars along this isochron, So for the star 1, it's still in main sequence, right? So you'll find it's show a quite high frequency. So the mu max is very high, so it's over 1,000 megahertz. But with the evolution for the subgiant number, for the subgiant star 2, it just show a little bit lower frequency, and the frequency keeps decreasing with the evolution. So that's so we can use this oscillation to decide where the star should be. So it's also a very important result for that. And also, if you go deeper, you can also distinguish the red giants, the hydrogen shell burning star, and also helium core burning star. You can also distinguish them. And also, I think the most successful example is helioseismology. So it's asteroseismology on the sun. And so in this very famous paper in 1985, so people just realized that we can measure the speed of sun in the solar interior and to get some information of the sun. And for example, we can measure the profiles of the sun speed, and also we can get the density and the temperature profile, and we can compare to the standard solar models. And we also can measure equation of state. We can measure the opacity and measure the helium abundance, which is impossible because there's no helium line for the sun. So, and it's a quite interesting history. So if you know this, there's a solar neutrino problem, right? So we observe, what we observe of the neutrino is not as many as the theory predicts. So someone will ask, is it because the solar model is wrong? Because maybe the sun is not as hot as we predict. But based on the helioseismology, we found no, it's not. So we just use an inversion method to reveal the internal structure of the sun. So it's quite interesting method. It's not like a forward modeling. So for the most of the technology we are using now is we calculate maybe thousands of evolutionary tracks and we find the best matching one. But for the inversion, we can get the model directly from the observation. We do not need to calculate we do not need to spend a lot of time on the code. So it's quite interesting technology. And so the top panel just shows the inversion of the sun speed, the deviation to the standard model. So you can see the square of the sun speed is consistent within maybe 0.4% of the standard solar model. And also in the bottom value is a density. It's a density profile. You can find that the density is consistent with the solar model within 1.5%. So it's quite accurate. So that means the solar model is correct. So now people know that there's a phenomenon called the neutrino oscillations. So that's new physics. So, and also we can calculate the internal rotation profile of the sun. For example, we found a very strong differential rotation layer at around 0.7 solar radii. It's called the tackle line. Maybe it's quite important to the solar dynamo mechanism. And we can find we can sketch a very good profile in the envelope, right? So you can see the core, the equator is rotating faster than the pole, and we can find differential rotation in this area. But this all come from PMOS, right? So for the sun, we cannot see GMOS. So you can see there's a blank area in the center of the sun. We do not know what is happening in the center of the sun because there's no GMOS detected. But if we look after the main sequence, if we look at the post-main sequence stars, that's another situation. That's the situation where we can see the GMOS. So because the GMOS cavity increased a lot and the PMOS cavity decreased a lot, so gravity modes can have the similar frequency as pressure modes. And if they have similar frequency, and in the middle they have a very thin evanescent region, that means this modes PMOS and GMOS can couple, can resonate. So that's called mixed modes, and we can use the mixed mode to measure the red giant stars from the center to the surface. And I recommend people to go to Joe On's seminar on the 1st of April. right? So, yeah, so it's not the festival, right? So so it's a true advertisement, so that they will give a more detailed introduction for the mixed mode. It's a very interesting area. So here is maybe I just give one example. It's my previous research. So we just discovered how the different rotation in red giant stars are built from main sequence to red giant stars. So in this figure, you can see the terminate age main sequence stars are on the left, and in the middle is a subgiant stars, and on the right is the stars at the base of the red giant branch. So you can see, and the y-axis is the ratio between the core and envelope rotation rates. So you can find a very clear increasing trend, right? So for the stars that are just leave the main sequence, they still show a rigid rotation. So that's the core have almost the same rotation rate as the envelope. But with the evolution in the subgiant stars, you can see that it's increasing. The core, the envelope is become slower and the core is faster. And in the red giant stars, they just show a ratio about 20. So the core is 20 times faster than the envelope. So that's an important result. Why it's important? Because if you know the theory predict the ratio should be 100 or 1000. So the core should be 1000 faster than envelope. But what we observe is just 10 times. So that's a very strong, inconsistency inside. So maybe we need more. We need some new mechanism to expand how the angular momentum is transferred from the center to the core. Maybe the magnetic fields. So we indeed observe the central magnetic fields in the center of the star. So it's we can observe the surface, the magnetic field on the surface, right, using the no matter Doppler imaging or the Zeeman splitting. But we can use asteroseismology to measure the center magnetic field. So that's what I did when I was in Toulouse. So we just found some weird rotational splittings. So if you still remember the rotational splittings, they show triplets because of the rotation, but the M equal 0 mode should be exactly in the middle if there's a pure rotational effect. But we just discovered several stars from thousands of stars that no. But we indeed found several interesting stars that the middle peak are shifted to the left, or sometimes they shift to the right. So that is a magnetic induced phenomenon. And we can measure two things. We can measure the field strength. So we found that the field strength is maybe about 10 to 100 kilogauges. So we can measure the field strength. That is the field strength in the hydrogen burning shell. It's not exactly in the center. It's in the hydrogen burning shell. It's just maybe 1% of the total radius of the red giant stars. And we also can measure. We also can give some clue for the field topology. We also can imply. We also can guess the shape of the fields of the magnetic fields. So this is a result. So maybe some stars are consistent with the dipole field, and we also can measure the dipole field, the inclination of the dipole field to the rotational axis. So if we have a dipole field that is aligned with the rotational axis, we have the A value of 2/5. And for this star in the bottom, maybe the dipole field is vertical to the field strength, to the rotational axis. And we also found that there are a lot of stars that cannot be explained by the dipole field. Maybe they show a more complex field shape. So it's quite an interesting result. Yeah, so as you can see, there are so many interesting results in solar like our oscillators. But I need to leave this area and we move to the main sequence oscillators. We just introduced a little bit about the delta scaling stars. So it is a main sequence pressure mode oscillators. So, and this is a typical power spectrum or amplitude spectrum for delta scaling stars. So I think the first impression for all of us is that is a complete mess, right? So there's so many peaks, and we don't know, we cannot find any pattern, we cannot find the equally spaced periods in this amplitude spectrum. So for a long time, we just do nothing for delta squigly stars. So we can do, what we can do is the high amplitude delta squigly stars. So just remember to go to our last talk in 20 minutes. But in 2020 in Sydney, Tim Badin just discovered several stars that show regular spacing right here. So you can see the peaks are regularly spaced, right? That is consistent with asymptotic relation, consistent with the solar-like stars, if you still remember. It just show constant distance between two peaks. So in this case, we can do some modeling. We can do some asteroseismology modeling for these stars. For example, we can measure the age of the main sequence stars. Before that, we can only use maybe isochron or some other thing to measure the age. But now we can use positions to measure the age. And we also can measure the age in open clusters and stellar oscillations using asteroseismology. That's a new application. And also we can use the positions as a clock of binary motion, because the positions in delta squigly stars are very stable. So sometimes you find that, so if we can measure the frequencies, amplitude, and the phase, right? But sometimes you find that the phase of the wave are changing. It's not because the stellar evolution. It's just because the binary. Right? So if the binary, if one component of the binary move close to you, the distance is shorter. So they just save the time of the light traveling from the star to you. But if the star move back, they have a longer distance to you. So the light should need more time to travel to the Earth. So that's why the phase is changing, and we can use this time delay to measure the binary motion. And in this case, we can measure, and this method is sensitive to the binary with long period, maybe the period of hundreds of days. So in this period region, it's hard to find, right? We can only use the radial velocity to measure it, but it's expensive, right? So now we can use this method to do that. Okay. So now we just move to the last part. It's my main research part. It's called Gamma Dorado stars. It's also a main sequence star, but the position is gravity modes. It's no longer pressure modes. And for gravity modes, we also show this regular spaced peaks. But be careful, the x-axis become period. So it's not frequency. We just calculate the 1 over frequency, and we got period. And for G modes, the peaks should be equally spaced in period. So we go this equation. We have this pi 0 over square root of L times L plus 1. So the pi 0 just give also is an age indicator. We can use the pi 0 to measure the age of the stars. But it's one interesting is that the GMOS is much more sensitive to rotation. So if the star is rotating very fast, the peaks are no longer equally spaced. So for example, you can see there's a very clear series of peaks, right? But the distance between each two peaks are decreasing, right? So you can see here is wide, but here is narrow, right? So this decreasing trend is caused by the rotation effects on TMOS. And we can use this phenomenon to measure the near co-rotation rates. It's not the surface line, it's not the outer envelope, it's near co-rotation rates of the stars. It's quite interesting. Here's one example. So in this figure, the young main sequence stars are located on the right side. So young stars on the right side, and the old stars on the left side. And we can find this decreasing trend, right? So the stars are slowing down in the main sequence from the beginning of the main sequence to the terminate age. But we also try to reproduce this trend using different models, and we found it's still some questions, it's still some problems about current model. So even in the main sequence stars, we are still not very clear how the angular momentum transport or redistribute within the star. It's also a large question, and nobody knows the answer. Okay, I guess it's the last page. I guess I gave a very short summary for my seminar. So we indeed can see waves propagating inside stars. So we can listen to the stars, like listen to an orchestra, right? Listen to a band, listen to music. And asteroseismology can tell us what stars are made of, right? We can measure the helium abundance, we can measure the equational state, and we can also measure the rotation and how the star evolved. And we also can give give clue for the physics processes operating in the star. For example, how the angular momentum is transported in the star. And also we have a very wide application to other research areas like the exoplanet, open cluster, and the galaxy archaeology, because we can get the age of the stars. Okay, thank you very much. This is all my seminar. I hope that everybody enjoyed.
That was really inspiring. I'm going to stop the recording so I can just ask questions. Okay, let's see. Maybe it's okay.